Welcome to the deep dive. Today we're jumping into some really potent ideas around writing better code and, boosting your productivity.
Mm.
Think of this as a way to get the key takeaways efficiently.
Yeah, that's right. We're working from a set of materials you shared, centered around the art of clean code.
Yeah.
We'll be digging into how complexity can really um, drag down efficiency, the 80/20
Wow.
principle, which is surprisingly relevant here than building an MVP, a minimum viable product.
Right.
And of course, the nuts and bolts of writing code that's, well, clean and simple to grasp. And maybe why jumping to optimize isn't always the best first step.
Exactly. So the mission today, really tailored for you listening, is to pull out those actionable bits.
Uh-huh.
We want you to walk away with stuff you can use now to code better, be more productive, sidestep common traps, all without getting, totally overwhelmed by jargon.
Let's do it.
Okay, let's unpack this. Starting with something I think everyone feels, the pain of complexity.
Yeah, let's get straight into that. So, complexity in programming, it's not just like intricate code. The book frames it as anything that's difficult to analyze, understand, or even just explain properly.
hmm
And that really hits you at every single stage of a project.
Oh, definitely. Even just planning something complex, suddenly estimating time, effort,
Yeah.
it becomes incredibly hard again.
Right, totally.
And then that just sort of ripples outwards. Defining requirements gets muddy. Designing it effectively is a huge challenge.
Oh, yeah.
And actually building it, that's often where you see like way more bugs, slower progress.
And it doesn't stop there. Think about testing. The more complex, the more interactions,
Uh-huh.
the harder it is to be sure it all works. The book had that neat Python example calculating RGB values.
Yeah, I remember that.
If you don't nail down the input types, like someone throws text in instead of a number, bam, you get errors you didn't expect.
Right.
Finding those needs really careful unit testing. You gotta check normal cases, sure, but also weird edge cases, bad inputs.
Yeah, the works. And deploying, oh man. Deploying complex stuff can feel like walking a tightrope.
Yeah.
Higher risk of things breaking, and rolling back is just so much harder if something does go wrong.
Yeah.
But it gets even more interesting because the book also looks at complexity from like the theoretical side, algorithmic complexity.
Yes. This is where we see how algorithm efficiency changes as the data grows. Those graphs you shared were super insightful comparing bubble sort, quick sort, and tim sort in Python.
Those graphs were stark, weren't they? You see
Well,
bubble sort just explode.
Yeah.
Its runtime goes through the roof as the list gets bigger.
Right.
Well, quicksort, and especially timsort, handle scale way, way better. Seeing the actual Python code side by side really connects the logic to that performance difference.
And it shows how what seem like small choices in algorithms can have massive downstream effects on performance and manageability,
Yeah.
especially with large data sets. That directly hits productivity. If your system's bogged down sorting inefficiently, that's time wasted.
Great point. And complexity hits us when we're learning, too, right? The book mentions this. Oh, yeah. Facing this massive wall of information, tons of interconnected parts.
Yeah,
It's easy to get lost, feel like you're spinning your wheels.
definitely.
The book kind of warns beginners against getting stuck in tutorial hell, trying to learn everything at once.
Mm-hmm.
Instead, it suggests focusing on simpler, hands-on projects first. Build that foundation. It's like trying to learn every screw type before you can even use a screwdriver.
Perfect analogy. It's that analysis paralysis thing. You spend so much time understanding you never actually do anything.
And it's not just code or learning, is it? The book brings up complexity in processes, too.
Right.
Like imagine booking a trip using 5 different websites versus just, tapping a few buttons on Uber.
Exactly. That simplification directly saves time and hassle.
We see it daily, too. Phone notifications buzzing, emails piling up.
Oh, yeah.
It fragments our attention, makes deep work so much harder. Our brains are just context switching constantly.
Yeah.
And I love that phrase, death by a thousand cuts. It's usually not one big thing, but all these little complexities adding up, right? They just grind down productivity.
That's it, exactly. A collection of small frictions.
So, okay, complexity's bad, we get it. How do we even start to fight back? Where do we focus?
Well, that flows really nicely into the next big idea, the 80/20 principle, the Pareto principle.
Ah, yes.
Basically, 80% of the results tend to come from just 20% of the effort or causes. The book gives some really diverse examples.
Yeah, it's wild how often it applies. Income distribution, like a small percentage earns most of the money. Happiness levels. Website traffic, you shared that table. The top 10 sites get, like, almost all the visits.
It's a staggering.
Book sales, too, right? A few bestsellers dominate. Even scientific papers, a small group of researchers often produce the bulk of the influential work.
And for us, coders, the key insight is for optimization. The principle suggests a small chunk of your code, maybe 20%, is likely causing 80% of the runtime issues. There was even that Pareto graph specifically for software optimization in the materials.
Yeah.
It visually shows that skew,
Right.
which is gold, really. It tells you where to look. Don't polish every line. Find that critical 20% that's the real bottleneck.
Makes total sense. Be strategic. Don't
Yeah.
just optimize randomly. And this connects to how we measure success too, doesn't it? Leading versus lagging indicators.
Ah, yes, that's a crucial distinction. Leading indicators are the actions you control that predict future success. Lagging indicators are the outcomes you see later.
Okay.
So for a researcher, writing high-quality papers is a leading indicator. The number of citations they get down the road, that's lagging.
I see. So focus on what you can actually do.
Exactly. Focus on improving those leading indicators. The actions and the good outcomes, the lagging ones, are more likely to follow.
And focus ties right back into Pareto. That Alice and Bob example is neat.
Yeah, showing how they focus their effort, programming, chess, politics. By concentrating on their key impact area, they got better overall results than if they'd spread themselves thin. Those bar charts showed it clearly.
Right. Focused effort gives disproportionate rewards. So for coders.
It means find that 20% of tasks that deliver 80% of the real value, whether it's features users actually want or fixing the biggest performance hogs.
Uh-huh.
The book even used the TensorFlow GitHub repo as an example. A small core of contributors makes a massive percentage of the commits. That bar chart and table really hammered it home.
Wow. And it's everywhere. You had that histogram for freelancers too. A small number do most of the gigs.
Yeah, it seems to pop up all over.
Right. It's like fractal or something. The 80-20 of the 80-20.
That's a great way to think of it. Pareto's fractal. And the book gives practical advice too, like reflect on your own work. What are your high impact tasks? Read more foundational stuff in your field.
Yeah.
Improve existing products that's often high leverage. And interestingly, it even suggested sometimes doing things that seem to reduce value, maybe to clear the clutter and see what's really important.
Huh. That's counterintuitive, but interesting. It forces you to reevaluate. Yeah. And there were links to articles for digging deeper too.
Yeah, on open source, income, Python freelancing, lots to explore there.
Okay, so complexity bad, focus good via 80-20. Now, when starting something new, how do we avoid building complexity right from the start?
Ah, that's where the minimum viable product, the MVP, comes in. It's a core strategy. The book paints a pretty bleak picture of the alternative, what it calls stealth mode programming.
Oh yeah, those diagrams were telling. You start with this grand vision, work in secret. Motivation drops, features creep in, timelines blow out, and then you launch this massive thing.
And maybe nobody wants it.
Exactly, because you had zero user feedback along the way. All that effort potentially wasted.
Precisely. So the MVP has 4 pillars, according to the book: functionality, design, reliability, usability.
Okay.
Focus on the core problem first. Just enough functionality to be useful to early users. Design it well, specifically for them. Make sure it actually works. It doesn't crash constantly.
Reliability.
And make it reasonably easy for those first users to figure out usability.
And the payoffs seem huge. You validate your idea early.
Crucial.
Get feedback while you can still change course easily, waste less effort on unwanted features, and you develop iteratively. Build, measure, learn, repeat. That feedback loop diagram showed it well.
Absolutely. Build, measure, learn. It just fundamentally de-risks the whole process compared to the stealth approach. Building in secret is just such a gamble.
Totally. The MVP gets you reality checks early and often.
Couldn't agree more.
So we know complexity hurts, we know focus helps, 80-20, and we know starting lean with an MVP is smart. Now let's get to the code itself, the nitty-gritty. Clean and simple code.
Right. This is the heart of it, really. The big message is write code for people first. For your future self, for your teammates, not just for the machine.
Because tangled, unreadable code is a nightmare to maintain later.
Exactly. Debugging, adding features, it becomes incredibly painful and slow.
So the book lists, what, 17 principles? We probably can't hit all of them, but let's just touch on some key ones. Like, think about the big picture.
Yeah, principle 1, just a reminder that code isn't written in a vacuum. It needs a purpose. It needs to solve a real problem within the larger system.
Makes sense. And principle 2, stand on the shoulders of giants. That feels very practical.
It really is. Use good libraries. Don't reinvent the wheel if a solid, tested solution already exists. Why write your own sorting algorithm when optimized ones are available?
Good point. Principle 3, code for people, not machines. Readability. This seems huge.
Absolutely core. And those examples were great, comparing X, D, Z to investments, yearly return years.
Oh, yeah.
The difference in immediate understanding is just night and day. Descriptive names are critical.
Bad names just add mental load, make you constantly translate in your head, which leads straight to principle 4. Use the right names. Clear, unambiguous, descriptive.
And even small things matter, like formatting. The book mentioned how inconsistent indentation can obscure names versus following PP8 for Python, for example.
Right, consistency helps readability a lot. Then principle 5, code tells the story. The structure itself should make sense.
Yeah, good code should almost read like prose, explaining its own logic. Which brings us to principle 6, comments. Always a fun debate.
Ah, yes. What's the take here?
Well, the idea is comments can be good for explaining why you did something complex or the high-level intent, but the goal should be code that's so clear it minimizes the need for comments.
So explain the non-obvious, but don't just repeat what the code says.
Exactly, and that ties into principle 7, avoid unnecessary comments. Don't state the obvious. Hashtag increment counter is usually just noise.
Got it. Principle 8, principle of least surprise. Code should behave predictably.
Yeah, no weird side effects or unexpected behavior that breeds bugs. And principle 9, a classic, DRY, don't repeat yourself.
DRY, fundamental. Avoid copy-pasting code.
Right. That miles to kilometers example was simple but effective. Put the conversion logic in one function. Easier to change, less chance of errors.
Makes sense. Principle 10, single responsibility principle. One reason to change.
Yeah, a class or function should do one thing. The book class example was good. Initially, it handled book data and printing. Separating printing into a printer class makes things more modular, testable, flexible.
Okay, then principle 11, just test. Write tests.
Non-negotiable, really. Unit tests, integration tests, acceptance tests. They ensure correctness and prevent regressions.
And principle 12, small is beautiful. Keep things small and focused.
Smaller functions, smaller classes, easier to understand, test, reuse.
Principle 13, law of Demeter. Talk only to immediate friends. That one's a bit more abstract.
It is. The coffee cup, coffee machine example helped. Basically, try to reduce how many different objects an object needs to know about directly. It leads to looser coupling, more flexible designs.
Okay, less tangled dependencies. Principle 14, GNI. Yanka need it.
Haha, yeah. Don't build stuff just because you might need it someday. Build what you need now. Avoid speculative complexity.
Good advice. Principle 15, avoid deep indentation. Readability again.
Definitely. Those nested if blocks become visually overwhelming fast. The example showed how refactoring to reduce nesting makes code much clearer.
And 16, use code metrics, like tracking complexity.
Yeah, tools can help flag potentially complex areas that might need simplification, like cyclomatic complexity, maybe.
And finally, 17, the Boy Scout rule, and refactoring. Leave it cleaner than you found it.
Love that one. It fosters continuous improvement. Every time you touch code, make a small improvement, rename a variable, simplify a condition. It keeps the code base healthy over time.
Okay, that's a great set of principles for clean code. But what about speed? Performance, that urge to optimize. The book had warnings about that, right?
Oh, big time.
Yeah.
The next section hammers this home. Premature optimization is the root of all evil.
Strong words.
Yeah. It's not that optimization is bad itself, but doing it too early, before you know where the real problems are, that often creates more issues than it solves. More complexity, harder maintenance.
Right. And the book listed types of premature optimization, like optimizing tiny bits of code.
Yep. Optimizing code per se, those micro-optimizations that barely move the needle. Optimizing function calls, like inlining without proof it's needed. Optimizing features, adding complex stuff for perceived future performance. Optimizing planning, over-engineering the initial design for scale you might never hit.
And just generally optimizing scalability too early. Also optimizing test design, making tests too complex before the core function is solid.
Exactly. And that story about Alice, Bob, and Carl developing the transaction system really illustrated it.
Right. Alice jumped the gun on optimization.
Yeah, she added that max transaction thing thinking it would help performance, but it just made the code more complex and harder to follow without actually solving a real measured bottleneck at that stage. The code snippets showed that contrast clearly.
So, when is the right time to optimize?
After you've identified a real problem, the book gives 6 tips for performance tuning, but emphasizes doing them after measurement.
Okay, tip 1.
Measure first, improve second. Use profilers. Find out where the code is actually spending its time. That CPU usage screenshot and Pareto-like chart showed how profilers pinpoint hotspots.
So back to measurement and data. In Pareto again.
You bet. Tip 2. Pareto is king. Focus on the 20% of code causing 80% of the slowdown. Don't waste time on code that runs quickly or rarely.
Makes sense. Tip 3.
Algorithmic optimization wins. Often, switching to a better algorithm gives way bigger gains than tweaking a slow one, like choosing Tim sort over bubble sort.
Right. Fundamental changes over micro tweaks. Tip 4.
All hail the cache. Caching is huge. Store results you compute often or data you access frequently. Avoid redoing expensive work. That Fibonacci example with and without caching showed a massive difference.
Yeah, caching is powerful. What else?
Tip 5. Perform computations offline. If something takes a long time, can you do it in a background job instead of making the user wait?
Good one. And the last.
Tip 6. Perform computations as they appear online. Similar to caching, pre-calculate results if you know you'll need them later, store them, and serve them quickly when requested.
Okay, so the overall message is clean code first, then measure, then optimize the bottlenecks, often using better algorithms or caching. Resist optimizing randomly up front.
That's the essence of it. Write it right, then make it fast where needed.
Got it. Well, that wraps up our deep dive into this material, doesn't it? We've covered a lot of ground.
We certainly have. From complexity being the enemy, to focusing with 80/20, starting smart with MVPs, writing clean code, and optimizing wisely.
So, quick recap for everyone listening. Complexity, bad for productivity. 80/20, helps you focus effort. MVPs, validate early, reduce waste. Clean code, essential for humans and maintainability. Optimization, do it carefully, based on data, after the fact.
Nicely summarized. And maybe a final thought to chew on. How could actively fighting complexity, even in small ways, every day in your coding, compound over time? Think about the gains in productivity, in code quality, with just one small step you could take today, right now, to simplify something you're working on.
Ooh, that's a great challenge. Food for thought. Well, thank you for joining us on this deep dive. We really hope these insights help you on your path to better, more productive coding.
Hope so too.
Until the next deep dive.